The most generic form of the chain rule says, suppose that we have a variable that is a function of m other variables, and each of those m variables is a function of n other variables, and it becomes very complicated very quickly. Instead, what I'd like to do is just demonstrate how we extend this to the next level, and then I will allow you to go ahead and extend it to whatever levels you want to beyond that. Suppose that w is a function of 3 variables, and each of those 3 variables is a function of 3 variables. What I'm going to do is simply draw a tree diagram so that you can see what such an abomination would look like. We're starting with w as a function of 3 other variables. Those variables are x, y, and z. Then each of those variables is a function of 3 other variables. Those variables being r, s, and t. The chain rule is going to work identically to how we've already seen it. If we're interested in a partial derivative of w with respect to any of the other independent variables, r, s, or t, it's simply a matter of following the branches from top to bottom. The 3 relevant partial derivatives we would be interested in finding would be the partial derivative of w with respect to r, with respect to s, and with respect to t. So, following each of these branches, there are 3 methods for how to get from w to r. W to x, x to r, w to y, y to r, w to z, z to r. Now, in order, that was the partial derivative of w with respect to x times the partial derivative of x with respect to r, or plus partial derivative of w with respect to y times the partial derivative of y with respect to r, or w to z and z to r. I guess generally speaking, if you were interested in finding the partial derivative of top variable with respect to whatever your bottom variable is, it would be necessary to figure out all iterations of the partial derivative of that top variable with respect to some intermediate variable times the derivative of that intermediate variable with respect to the bottom variable. Once you've figured out all possible iterations of that, add them all up. So there's your, I guess, most generalized version of the chain rule. As it applies in our case, to get from w to s, we can go from w to x and x to s. We could go w to y, y to s, or we could go w to z and z to s. And finally, to go from w to t, we can go w to x, recycling that partial derivative once again, and then x to t. Or we can go w to y, y to t, or we can go w to z and z to t, turning these 3 partial derivatives into, well, 12 different partial derivatives that you would have to do. A couple of them do get reused though, because there are 18 total partial derivatives on the right hand side, but some of them get repeated a couple times, specifically the partial derivative of w with respect to the 3 intermediate variables. Now for those with any sort of training in linear algebra, you'll notice that what we have here looks an awful lot like matrix multiplication, where we're multiplying the same 3 things together and then adding them all up. That's not a coincidence. They are very closely related to each other, and if any linear algebra students would like to inquire about it, I would encourage you to do so during my office hours.